Hello everyone, the problem that we're looking at today, this one's special. It's the USACO 2025 US Open Contest Gold Problem 1 of mu decomposition. So this is the contest that just ended 2 days ago, and I screenshotted the problem so we can look at it now. So if you haven't taken the gold, you can read this problem statement yourself first. It is quite simple. You are given a string consisting of only M and O, and then you're trying to split the string basically into a bunch of mu's where each mu is an M with K zeros, K O's behind it. And now you're trying to determine the number of ways to divide this big sequence of M and O into mu with exactly K zeros, with K being given and the length of the string can be very long. So you are given an integer L representing how many copies of the string is given, and you're given the first part of the string. So basically you have a string of length 10 to the 6th power, and then you repeat that string several times, at most 10 to the 18th times, until you get the entire string, and then you try to decompose it into a bunch of mu with exactly K zeros. So a sample will be right here. You have this original string has length 6, so it's mu, and then each mu has to have 2 zeros, and there's only one copy of this string, which is why there's only one way to do this. And another sample would be, see, that's the first one. Another sample would be this one. You have MMOO, where each mu only has 1 0, so there's 4 ways to do it, since there's 2 copy of this MMOO, the string, because it will be the first M with the first O, and second M with second O, and third O, fourth M, fourth O, and then you can just switch around the order of M's and O's, and in total there's 4 ways to do that. And then if you do the exact same string but with 100 copies, there will be this many ways to do it. However, you have to take the answer modulo 10 to the 9th power plus 7. So you can pause the video once again and think about this problem yourself. Okay, so my solution is actually quite straightforward. So we have a bunch of strings, and it is guaranteed. The first key notice is that it is guaranteed there is at least one way to decompose it. It is guaranteed that the number of decomposition of S is non-zero, which means that the ratio between the number of M and the number of O in this sequence has got to be set, right? Think about it. For the first copy, like before we copy L times, for this first copy of string with a length N, there has to be exactly K times as many O as there is M. So with this being said, since we know that the string is decomposable, we know that all the M's must be paired with all the O's within each copy of this string of length N. Because think about it, if we make a drawing here, okay. We have M, let me just use a sample here actually, OO, and M, OO, and say that's the first copy. We know that, say we start from the end, right? All the M must be matched with all the O in each copy, because we know that there must be, so the number of O must be K times number, oh, that's a bad number sign, number of M, because it has to be in order for there to be at least one valid decomposition, which means that once we get done with, say there's a bunch of other copies over there, once we get done with all of them, there must be no O left and no M left, because they must pair exactly. Which, with that being said, we know that this singular copy wouldn't affect any later ones, and it wouldn't be affected by any earlier ones, so all of them are completely independent of each other. So with that being said, the amount of different decomposition we can have for this entire string with L copies, with L being very big, is actually just the product of the number of ways to do each individual string. And each individual string only has a length of 10 to the 6th power. So we can actually easily calculate that. Because think about it, for every single M is just the number of ways to choose the O's behind it. And say we have a few more O's, so it's, and say K is 2, right? So we need 2 O's behind every M, and every time we reach an M, we keep track of how many O's there are left, and then it's just the number of ways to choose 2 O's out of a total of 4 O's, which is, in this case, what? 4 times 3 divided by 2 times 1, which is 6 ways. right? So 6 ways for this M to choose, and then we cross out 2 O's, so now there's only 2 O's left, and then we have this M choose another 2 O's, so this time is 2 choose 2, right? And that is one way, and we multiply them, we get there's 6 ways to do in this one copy, and say we copy this 3 times, then the total number of ways to decompose this whole string is just going to be 6 to the third power, which is equal to something, right? So after knowing this problem becomes very simple. We just need to calculate the number of ways to choose a certain number from a certain number, which can be easily calculated using a pre-calculated array for factorials, which is what I did here. FAC is the array for factorials, and since we know there can be at most n O's in this whole string, I mean in every copy of this string, obviously, but then we're just considering every copy independently as the whole string now. So there can be at most n O's existent. So the most factorial we need to take is n, so then that's why we pre-process all the factorials below n, and remember to take mod of p on the way. And then obviously you have the fast power, because in the end we have to be multiplying all the answers together. However, notice that since we're taking modulo of p on the whole way, we can't just do the n choose m process like we do before, because there's division involved, which means we need to use Fermat's-Little theorem to find the multiplicative inverse of a number and multiply the first number by the multiplicative inverse of the second in order to achieve the effect of the first one divided by the second under modulo p. If you don't know Fermat's-Little theorem, go search it up. I have not made a video on that yet. And the rest of the process is just straightforward. The factorial for the top, factorial for the bottom, and then you multiply them, except the second one is actually a multiplicative inverse. And then you subtract the count of total amount of O's that you still have to be paired with M's by K, because this M took K O's. And then if there's O, we don't pair it. Instead, we just add 1 to the count of number of O's that existed currently, and then we take the answer to the L's power, because we know that all of these strings are completely independent of each other, and if one has ans possibilities, then 2 have answer squared, 3 have answer cubed, so then it's just answer to the L's power, and then modulo p, of course. And there you have it. Under 30 minutes, you had the first problem of the USACO 2025 US Open Gold Problem 1. You have it solved. That is it. Thank you for watching, and hopefully you can solve this problem now after this video. I would say it's rather easy for a US Open for a gold, especially 2025, at least for me. I don't know about other people, but I think this solution is quite straightforward. The only thing you might have to notice is that the number of M is always consistent with the number of O within each copy of the string, so that each string is independent of each other. And after that, it's just straightforward. Okay, so hopefully this video helped. Thank you for watching, and I'll see you tomorrow. Alright, so that was a problem review, and now it's a gap time. So if you were just looking for the solution of this 2025 US Open Problem 1, you can go ahead and click out of this video. So I would say I did decent on this 2025 US Open contest, because in total I got 480. Other than this problem, I was also able to, this one, I was also able to get half credit on the problem 2, and I was able to get 1 test case in problem 3. So with that being said, I have a total of 480 points, which is not good, definitely not enough for promotion, but not bad for the first gold, I'd say, considering my first silver was 300 points, and on average, when you just get promoted, 300 would be a good score. So yeah, 480, pretty good. And the first problem was really, really surprising. I was not expecting to solve it, especially not under 30 minutes. Because as you can see, my first submission is at 12:31:13 Eastern Time, which is exactly 30 minutes after the test has been released. And I started the test about 3 minutes late, so that's about 30 minutes into the entire contest. And this is a certified score, though. So that just proves that I actually solved the thing within 30 minutes, which is completely crazy. But now that I think about it, I think this problem is, at least for me, sub-silver level. It is definitely easier than both problems from January silver. Probably quite a bit harder than the one from February silver, because, February was way too easy. I don't know, maybe on par with the December one from this season. but for gold, it is way too easy. The second problem, I actually surprisingly also knew the solution to it, except I forgot how to write a segment tree and had to write a tree array instead. I mean, binary index tree. I keep calling it tree array. A binary index tree instead, and that took an extra log of complexity maintaining dynamic prefix max. So I would have gotten this problem if I knew how to write dynamic prefix max with segment tree, but unfortunately I don't. So there you have it. 480 points, first gold, not bad. I would say at this rate, I can probably get platinum next season. Not sure about December, but anyways, thank you for hearing me yap about this, and thank you for watching, and I'll see you tomorrow.